Welcome to EDU World Space.
The first part of this question asks us to draw a principal ray diagram, and because I am doing it on my computer, it's not going to be very to scale. So I would recommend you do this on your own on a piece of paper with a ruler. That's how it comes out the best. But what we're given is an object to the left of a convex spherical mirror, and I'm just going to label the points C, which is the center of curvature, and F, which is the focal point of the mirror, which is half the distance between the vertex and the center of curvature. So we want to draw the principal ray diagram, and we'll color code that. There's 4 different types of principal rays. The first one we're going to draw is light that is hitting the mirror from a direction parallel to the optical axis. And so it's coming in like that, and we know that it's going to be reflected back as if it was coming from the focus. So it'll come off in that direction like that. Now in green, if we have light that is coming from the object towards the mirror as if it was going to hit the focus like that, that will be reflected back parallel to the optic axis. And if we extend that ray behind the mirror, we see that we get a point of intersection right there. Now, just to make sure that point of intersection is actually correct, we're going to draw a third type of principal ray, which is the ray that comes from the object as if it was going to hit the center of curvature, like that. And we know that it would be reflected straight back where it came from. And if we extend this out, it goes through the point, it goes through C, and we see that we have another intersection at this point. Now the fourth ray, which I'll draw in black because I've run out of colors, is coming from the object, and it hits the mirror exactly at the vertex, and we know that it will be reflected back out at the same angle just below the optic axis instead of above it. So that angle is the same. And if we extend that back like before, we see it also goes through the point, which means this is where our image is going to be. So what do we know about the image? The image from this ray diagram, we expect the image to be virtual because it is behind the mirror, it's to the right of the mirror, and we expect it to be upright. So let's look and use actual numbers to see if these intuitions are correct. So let's go over what we're given in the problem. So the givens are, we know the object distance, which we'll call S, is 16.5 centimeters. We know that the object height, which we'll call Y, is 0.600 centimeters. And we also know that R, the radius of curvature of the mirror, is 22.0 centimeters. But because it is a convex mirror, we're going to say that is negative. And from this, if we remember that the focal length of the mirror is equal to the radius divided by 2, pretty easily in our head we can see that the focal length is negative 11.0 centimeters. So what do we want to find? What we want to find is S prime, the image distance, and Y prime, the image height. And we're going to find these using 2 equations. And these equations are 1 over S plus 1 over S prime equals 1 over F. And the second equation is M, the magnification of the mirror, is equal to the image height divided by the object height, and it's also equal to the opposite of the image distance divided by the object distance. So first, let's find the image distance. So how far away the image is from the mirror. And so just to remind ourselves, we have this, we're going to be working with this formula. 1 over s plus 1 over s prime equals 1 over f. And we know that s is 16.5 centimeters and f is negative 11 centimeters. So let's play around with this formula. We want to find s prime on its own, so we can subtract over the 1 over s. So we end up with 1 over s prime equals 1 over f minus 1 over s. We want to make this into a single fraction to make our lives easier. So we'll multiply 1 over f by s over s, and we'll multiply 1 over s by f over f. And we end up with s over f times s minus f over f times s. And if we combine that into one fraction, s minus f over f times s. And that's equal to 1 over s prime, the image distance. So to find s prime then, we just take the reciprocal. And that means that s prime is equal to f times s over s minus f. And we know both of these numbers, s and f, so we can just plug them in. And we get that minus 11 times 16.5 over 16.5 minus 11. And just plugging that into a calculator, we get that s prime is negative 6.6 centimeters. I'll box that in red. And if we think about this answer for just a second, we see that we have a negative sign here. And so that means that the image is virtual, and it's to the right of the mirror. Okay, so that's the first part. The next part, we want to find, we want to use this equation, the magnification equation, to find the image height, y prime. So to remind ourselves of the formula, it's equal to the image height divided by the object height, but it's also equal to the opposite of the image distance divided by the object distance. And remember that we know y, s prime, and s. So first let's find m. So m equals, we know both s prime and s, so we can find what m is, and so that's going to be equal to the opposite of minus 6.6 divided by positive 16.5. The negative signs cancel each other out, and we end up with a magnification of 0.4. Okay, now we plug that back in to the first part of the equation, and rearranging that, we can see that the quantity we're looking for is the image height. Y prime is equal to the magnification times the object height. And so we know both of these numbers as well. So we end up with 0.4 times 0.6, and that equals 0.24 centimeters. I'll box that because that is our solution for the image height. And just like before, let's look at the answer and see if it makes sense. We look back at the beginning, we wanted the image to be upright. And because this is positive, this answer gives an upright image. And so at the beginning, we wanted a virtual upright image. we found that the image is virtual when we found the object distance, and we found that it was upright when we found